Look at the sheer mass of this ship. Building something at this scale requires thousands of tons of steel, highly specialized equipment, and hundreds of workers to converge on a single stationary coordinate. Many assume designing the space for an operation like this is a matter of architectural aesthetics or simply making a workspace look organized. It is not. A facility layout is the physical hard coding of an organization's strategy. It dictates exactly how time and capital move through a business. The core mechanic is strict. Where you place your transforming resources, the static machines, equipment, and staff, absolutely dictates the flow of your transformed resources. Those are the raw materials, the streams of data or customers moving through the system. Place those machines poorly and the flow paths clash. Materials stack up in queues. Work-in-progress inventory swells and throughput drops. Every second a component spends in transit between workstations is a measurable financial penalty. Eliminating that penalty makes spatial arrangement a rigorous, mathematically driven engineering discipline. This chart displays the volume variety matrix, the foundational law of operational design, mapping production volume against product variety. In the top left quadrant, we find very low volume but extremely high variety. Think of a shipyard building customized vessels or a hospital treating unique cases. Because specific requirements change with every order, the flow of resources is irregular and unpredictable. The physical layout must be highly flexible to absorb that chaos. The opposite extreme lies in the bottom right. Here, variety is near zero and volume is massive. You are producing identical units by the millions. There is no need for flexibility. These operations demand rigid, specialized layouts engineered specifically to force smooth, continuous, identical flow. To understand how facilities are built, we have to look at how engineers translate these exact volume and variety coordinates into 4 foundational geometries and the mathematical rules they use to optimize them. The first geometry maps directly to the extreme of high variety and low volume. It is called the fixed position layout. In this model, the transformed resource, like a hydroelectric dam or a commercial skyscraper, is simply too large or fragile to move. It remains entirely stationary. Because you cannot arrange the product, optimization focuses entirely on the logistics of moving everything else. Engineers rely on techniques like PERT and CPM. These are critical path scheduling tools that calculate the exact mathematical sequence and timing of interdependent tasks, ensuring specialized cranes, cement mixers, and labor teams do not deadlock on a single site. Moving down the matrix to medium-high variety, we encounter the functional layout. Here, resources are grouped strictly by their specialized function. We see this heavily in services and batch manufacturing. Customers or materials bounced intermittently between specialized departments depending on what they need. A customer at a bank might visit the deposit teller, then walk across the lobby to a loan officer, then head to a vault. This diagram is a load matrix. It tracks the exact number of times a resource travels between these 4 distinct departments over a given day. By multiplying the daily volume of trips by the physical distance between the departments, we expose the total operational inefficiency. To fix this, industrial engineers deploy algorithms like CRAFT or ALDEP, computerized models that systematically test thousands of department configurations. They swap block positions over and over until they find the arrangement with the lowest possible physical distance for the highest volume of traffic. Optimizing a functional layout is an exercise in identifying and eliminating physical transit friction between siloed departments. Operations sitting exactly in the middle of the matrix, medium volume and medium variety, use a hybrid geometry called a cell layout. Instead of separating machines by their function, a cell layout abandons the silos. It physically groups a specific set of dedicated machines and workers together into a self-contained unit to process a specific product family. To figure out which parts belong in which cell, analysts use a technique called production flow analysis, or PFA. This is a component machine matrix. It starts by plotting every single part a factory makes against every single machine required to build it. At first, the data looks like random noise, but by algorithmically rearranging the rows and columns, PFA looks for hidden dependencies in the manufacturing steps. When the data points finally cluster together into solid blocks, they mathematically prove that certain groups of parts use the exact same cluster of machines. High-performance manufacturing cells are derived directly from these mathematical dependencies, stripping away unnecessary transit between distant ends of a factory floor. Finally, we reach the extreme bottom right of the matrix: extremely low variety and massive volume. This is the domain of the product layout. You know this as the assembly line. Transforming resources are arranged sequentially, strictly following the logical steps required to build one specific thing. The goal is continuous, unbroken, automated flow. No batching, no intersecting paths, and no variations. Because the line moves continuously, the absolute bottleneck is time. The core engineering challenge here is called line balancing. This diagram shows the calculation for cycle time. By dividing the total available production time by the required number of units, engineers establish a hard threshold. This is the absolute maximum time allowed at any single workstation on the line. Engineers must then slice the total manufacturing process into individual work elements and drop them into sequential stations. The objective is to pack each station with tasks exactly up to the cycle time limit without breaching it. But tasks rarely divide perfectly. The remaining gap between the allocated work and the cycle time limit is called balancing loss. By adding up the idle seconds across every workstation every single time a product advances, you find the percentage of wasted, unproductive capacity. At mass production scales, where millions of units are processed, eliminating a fraction of a percent of balancing loss heavily dictates the entire facility's profitability. All of these optimization heuristics assume a frictionless, perfectly reliable environment. Reality rarely complies. Consider infrastructure constraints. In regions dealing with unreliable power supply, like load shedding in Southern Africa, highly synchronized systems face sudden cataclysmic failure. To survive environmental friction, engineers have to make a strategic choice between two layouts: a long thin process or a short fat process. This diagram illustrates a long thin process, the peak of theoretical efficiency. Work is divided into small, specialized, sequential stages, but it has zero robustness. Because every stage depends on the previous, a single point of failure stops the entire line. The alternative is the short fat process. Work is consolidated into fewer, broader stages, and equipment is duplicated to run parallel lines. You lose the extreme speed of hyper-specialization, but gain redundancy. If a machine breaks down, the other parallel stations keep processing. Effective operations managers routinely choose to degrade peak theoretical efficiency. They sacrifice speed to buy survival. Physical layouts also face disruption from technological shifts that eliminate the need for physical space altogether. Take a legacy service operation, like a bank processing mortgage applications. Traditionally, this required a massive functional layout: vast rooms of filing cabinets, separate floors for data entry, and couriers physically moving paper between specialized departments. When that bank digitizes the application process, the physical functional layout instantly collapses. The transformed resource, the customer's data, no longer moves through hallways. It flows through automated validation systems, resembling the high-speed, continuous flow of a product layout. Throughput surges and real estate costs vanish, but the bank trades physical transit friction for new, systemic vulnerabilities. A local bottleneck at a filing cabinet is replaced by the risk of total server downtime or severe cybersecurity breaches. The perfect layout is never a static map. It is a continuous, data-driven negotiation between the precise mathematics of flow and the unpredictable friction of the real world.